But before I get to the talk, just a short introduction about who I am. I'm Prajwal. I am mainly a Go and Rust programmer, and I completed my Google Summer of Code in 2022 and 23 with CRIU, which is why I picked this as the topic for today's talk. And I'm currently working with the D Language Foundation on a freelance compiler project. You can find more details about me on my website. I'll be sharing the slides with you all. So, do we wait or do we start the talk? All right, let's get going. So, let's just try to understand what checkpoint restore is as a general topic. So, I'm sure all of you would be aware of deployments, and you would all be running services, where at some point you would have felt the need to want to take a snapshot of something and save it to disk. Maybe you just want to stop something that's running, you want a pause button, after which you can continue a little later. Or maybe you just want to take something from one computer and just move it to another. So checkpoint restore is basically the act of taking a process, identifying everything that's associated with it, and writing that to disk. And then you can use these files that are saved on disk to restore it on the same system, a different system, in a different scenario. It's whatever that's your fancy, So let's look at why checkpoint restore is important. So as you're all aware, I'm sure everybody has at some point broken something while working at office, right? So as software engineers, none of us are perfect, and software breaks all the time. So checkpoint restore gives you the opportunity to insure yourself against mistakes that happen. And another aspect is that backups are hard. Taking backups is really difficult, as you're all aware. So generally, when you hear the concept of backups, we usually back up data. So backing up processes is something that's less common. And checkpoint restore allows you to do exactly that. You can take a process that is running and create a backup of that process. A stateful backup, exactly the way it was. And later you can resume that from that particular state. Another aspect would be security vulnerabilities. Let's say you have an exploited container that's running on your production cluster, or you have some service with a vulnerability that's recently been exploited. And you don't want to shut it down immediately. You want to debug this. You want to look into it. You want to see what can be done and what did I do wrong. So you can checkpoint it, spin it up in a sandbox, and that gives you the opportunity to explore it in an isolated environment without affecting the rest of the things that you're doing. And long startup times, how many of you have waited 1 minute, 2 minutes, 3 minutes after applying your Kubernetes config, and you're just like, oh, when is this service going to start? So another thing you can do with checkpoint restore is you can start something up, you can warm it up, you skip the cold boot state, and then you checkpoint it. So the next time you want it, you just spin it back up exactly from where it was supposed to start, rather than starting it from scratch all over again. And reproducible state. So as you're all aware, updates generally tend to break things despite their best intentions. So imagine being able to take everything that you're running, creating a perfect copy of it, doing all sorts of experiments on it, making sure nothing breaks, and then being able to do that knowing that nothing is going to break on your production cluster. These are just some of the things that checkpoint restore allows you to do. So there are multiple different tools available in the software world today that allows you to do checkpoint restore, but there is one particular tool called checkpoint restore in user space. It's abbreviated as CRIU. And this is acknowledged as being the most complete solution out there for checkpoint restore. It's available on Linux as of now, and it works in almost every possible case that you can think of with Linux processes. So how exactly does CRIU as a tool work? So how many of you here are familiar with the internals of the Linux kernel, or have worked with the kernel before? Can I show of hands, please? Okay, so for those of you not aware, the Linux kernel offers a feature called ptrace. So ptrace stands for process trace, where you have a parent process, And you can use that to attach it to a child process. And it allows you to intercept every syscall that the child process makes. And everything that the child process is doing is visible to this parent process. So what CRIU does, it attaches itself to the parent, it attaches itself as the parent process to the process that you want to checkpoint, and then it walks the process tree and freezes it completely. So now, if you have a parent process, that process itself and every single child process spawned by it is now frozen. And after this, it does something very, very creative. Using ptrace, it injects parasite code into the memory address of the process that you're checkpointing. And effectively what this does is, it gives you unrestricted access to the memory contents of the process that you're trying to checkpoint. So using this, you get access to every associated resource of the process. You can see all the sockets it's operating with, all the files it has opened, the particular memory location that's accessing, stuff it is stored in memory, files it has written to on disk, and the list goes on, every possible associated resource. And then it serializes this data into a bunch of binary files. It uses protobuf for serialization. And it gives you a neat folder with a different file for each type of data. So you have one file that stores the PIDs. You have one file that stores the process tree. You have another file that stores the memory contents, and so on. And then you just remove this parasite code from that process and detach yourself from it. So in a completely isolated and completely sanitary way, CRIU goes in, checkpoints a process and its entire process tree, and then comes out of it. And it does not affect the state of anything else that was associated in that particular namespace or in that particular C group. So why is checkpoint restore hard? There are a lot of things that happen on a low level. So those of you who work with low-level programming, you know how fiddly it is. There are things that change across architectures. There are things that change across distributions. And keeping things consistent is a really, really big challenge. So one of the main challenges that was encountered with checkpoint restore is libraries. So let's say you have a process that's using a dynamically linked library, and you want to checkpoint this and restore it in a different environment that is using a different version of that same library. Now, this is not going to work because the memory addresses that the process refers to is not going to be the same across different versions. So the major challenge is that the environment in which you perform checkpoint and restore must be consistent. If you're performing checkpoint in one particular environment, it needs to be almost identical. You can get away with a few smaller details, but it needs to be almost identical for you to be able to safely restore it. And since CRIU checkpoints the entire process tree, it maintains the relations across the parent and the children in the process tree. So a side effect of that is that the PIDs must remain consistent across the process tree. Let's say you perform a checkpoint and you have multiple processes. You decide to tweak the PID of one process. Now, you may be able to restore that process correctly, but you might not be able to restore its children because they don't know which PID to refer to as the parent. And again, going ahead from the same point, you cannot checkpoint isolated parent processes because CRIU checkpoints the entire process tree. So you cannot, remove just the parent process and ignore the children. And another important point to note is that the Linux kernel allows any process to attach using ptrace exactly once. So you have certain tools like GDB, strace, which use ptrace internally to give you the functionality that they offer. So if you want to checkpoint those, it's not possible because they have already ptraced the child process. And when CRIU tries to checkpoint them, it's going to try to ptrace that again. And that would not be allowed by the kernel. So yeah, a lot of things can go wrong, and it's pretty easy to mess this up. But it's OK. This is fine. So coming to the Go side of things, Go today, as we all know, in the DevOps ecosystem, Go is the really big player. Docker, Containerd, LXC, Podman, Kubernetes. The list goes on. Every major DevOps tool today is written in Go. And the challenge of integrating checkpoint and restore with Go into the DevOps ecosystem simply gets harder because you have multiple layers to make it work on. So this is the structure of a typical Kubernetes node. You have the node itself, which is one system, and then you have a kubelet, which is the node agent for Kubernetes. And that interacts with a high-level container runtime, which is typically container D or CRIU, which then interacts with a low-level container runtime, which is typically runC. So now, let's say you want to perform a checkpoint on one single pod. So what do? You need a Kubernetes API that you can hit saying, hey, I want to checkpoint this. And then that will be communicated to the kubelet, which needs to call a similar API on the high-level container runtime, which needs to call a similar API on the low-level container runtime, which then calls CRIU to perform the checkpoint itself. So you can understand how much of a challenge it is, especially with how quickly things change in today's landscape. You need to provide consistent APIs for checkpoint and restore across 1, 2, 3 layers of the ecosystem, and make sure they're all interoperable, make sure they're all compatible with each other, and that there's something the user can conveniently use. So yeah, things just get harder the larger you go in scale with checkpoint and restore. So GoCRIU is a library that was created to natively integrate CRIU with Go projects. So there are two main sub-libraries that are provided by this library. phall stands for process hall, and it's a solution that you can use to perform live migration of containers directly from within your Go program. So you do not need to deal with, invoking CRIU manually. You do not need to deal with CRIU RPC calls. You don't need to deal with any of that. The phall library does all the heavy lifting for you. You create a client, you create a server, and boom, you can just shoot a container from one system to another. It's a complete breeze. And the second library that's offered under GoCRIU is crit. So this was the library I developed during Google Summer of Code 2022. And it's a Go library that allows you to manipulate and inspect an existing checkpoint along with its images. So what do I mean by this? Let's say you checkpointed a process, and you want to do some fiddly stuff with it. The next time you restore it, you don't want it to open the TCP connection that it opened the last time. You want to restore it with a different set of files that it's accessing compared to what it was accessing previously. Or maybe you don't want it to have access to certain memory locations that it previously had access to. So crit allows you to do that from within your Go code. It allows you to fetch the contents from a checkpointed image, see what is there in it, deserialize that to JSON, edit it however you want through a native Go struct, and then write that back to that file. So this gives you unlimited freedom within certain bounds to manipulate your checkpoints and modify them before you perform your restore. So in case you know that you're performing checkpoint and restore across two different environments and you know the differences, you can use this to resolve those differences and ensure that your restore works. And this library is currently being used across multiple projects. So runC, LXD, Podman, Checkpoint CTL, and also most recently Kubernetes has also used this library to provide native support for checkpoint and restore. So what are the possibilities you can do with checkpoint and restore and Go? So there are some really cool creative things you can do. Like I mentioned towards the start of the talk, blazingly fast startup times. So you can start your services that require a cold boot, warm it up, and after the warm up is done, you can checkpoint it. The next time you need to bring up that process, just start it from the warm start state. It's going to be a stateful checkpoint, which means any data that you have already initialized, any caches that you've already built, all of that is going to be statefully saved, and all of that is going to come back up exactly the way it was when you perform the checkpoint. And the second thing you can do is live migration of containers. This was the main motivation behind creating CRIU and GoCRIU. So live migration of containers is this act where if you have multiple nodes on which you're running your cluster, and for some reason you need to shut down one particular node, or one particular node is not accessible, you can take a container that's running on it and instantaneously move it to another node without affecting whatever is running within that container, and without affecting how that container interacts with other containers in its ecosystem. And forensic analysis of containers. So like I mentioned earlier, you have a vulnerability, you have some security issue, and you want to debug this. But you don't want the process you're running or the container that you're running to realize that you're trying to debug. So what you can do, you checkpoint that container and you spin it up in a sandbox. Now, because of the way CRIU performs checkpoints, the container itself doesn't realize what's going on. It thinks it's in the exact same scenario it was previously. It thinks, oh, I have a lot of other containers I'm connected to. I have all my ports open. I have all my network connections available, all my files available. But you have spun it up in a sandbox, and you're free to experiment and pen test as much as you want along with it. And this gives you the freedom to fearlessly ensure that you can debug your vulnerabilities without ending up affecting your production cluster because of error propagations. And stateful reboots. How many times have you had to do a kernel upgrade on your production cluster? And you're like, oh no, I need to switch everything off, switch everything back on, and make sure it's all working. So checkpoint restore makes it trivial to do this. So you statefully checkpoint all of your containers. You perform an update on the base image, and then you just statefully restore all the processes back up. Although the base image changes, nothing else changed. All your upper layers are still working the same, and they don't need to know about these base layer changes, right? And the last use case is dry run of updates. So along the same lines, let's say you have a really major update. You're doing some really big breaking changes. You can checkpoint your entire Kubernetes cluster, spin it up on an alternative set of nodes, and do your update. If you know nothing breaks, you can actually apply that to your production cluster. So it just makes it a breeze for you to do things without breaking and maintain consistency across your deployments. So let's have a quick demo. I'll just show you guys some of the possibilities of what can be done using the GoCRIU library. Is the font big enough for everyone to see? Right. So let me just run. So how many of you know about HTTPD here? How many of you have heard of HTTPD? All right. I'll not go into the details, but I'm just using HTTPD as an example process here so that I can show you some of the nicer features of what can be done with GoCRIU. So I'm just running a very simple container. It exposes one port, port 8080. And so the way you do this works the same across all your container runtimes. Podman, Docker, they all use the same commands. I'm just using Podman for convenience. So if I do Podman PS, you can see that the container is running. And now if I do Podman container checkpoint, so basically what the flags are doing is -k is saying that keep the temporary files that are being used for performing the checkpoint, and -e is just allowing me to export that into a tar archive. So now when I do this, it's going to take a little bit of time, but I hope I did hit enter. That's taking slightly longer than expected. Yeah, there we go. So now if I do Podman PS, you can see that the container is not running anymore. So where did that container go? I now have a tar archive containing that container along with every single process running inside it in exactly the same state it was. So if we see the files inside this, so you can see there are a lot of files here. Basically, the checkpoint folder contains the core images that are provided by CRIU regarding the process. So you can see a lot of core files. So this stores all the important information about every single PID. And oh, that's a lot of files. So you have a cgroup.img. That stores information about the C groups that were created within the container, what processes were inside of which C groups, and how each of these C groups had restrictions imposed upon them. And you would also have FD info that contains file descriptor information. So every file or socket that has been accessed and opened by that process is present in this. FS, that's file system information. You have memfd, which is the memory locations accessed by these file descriptors. You have MM1, 2, 3, 4, 5. Those are memory maps. So that is literally the entire memory space occupied by a process, checkpointed and present in this file. So let's just see how we can conveniently view some of the stuff here. So Checkpoint CTL is a tool that was created recently using the GoCRIU library, and it's mainly a tool for forensic analysis of containers. So you can see how Checkpoint CTL show tells me what container I've checkpointed, what engine was being used to run that container, which image was being run, and a few other details, what runtime was being used and the size of the checkpoint and all that. But the really cool part comes with all the flags offered by a subcommand called checkpoint CTL inspect. So if I do checkpoint CTL inspect without any flags, it's going to show you this kind of a tree. So it just says the same information that was shown by checkpoint CTL show, but as a tree. But now, if I want to see the process tree of what was checkpointed, I can do PS tree. And now, you know that the container had one parent process spawned by HTTPD, which had 3 more child processes which were identical. Okay, let's say I want some more information about this. I want to know every single environment variable that's being accessed by these processes. So I can just do PS3 env. And now, for each process, you have a list of environment variables that was set by the process, that was accessed by the process, and that's being used by the process. And the limits are nil. For the possibilities are nil for what you can do with this. Let's say you want to view what files have been accessed by this. So I can do files. And this tells you what kind of file and where the file was located. So it tells you there are 2 pipe connections opened by one of the process, and it's accessing /dev/null. And it's also using Apache to serve. And that is the current working directory. And where is the root directory from which the process is running? That is just /. And it also shows you the sockets. So sockets are just special types of file descriptors in Linux. So it also shows you the sockets that are being used and what kind of socket is being used. So you have an inet socket, 2 of those, and it tells you the file descriptor being used by those inet sockets. Now let's say I want to go into more detail about these sockets. I can just remove this flag and put sockets. So now, it's going to give you detail about the sockets being accessed by each process. So you have a TCP socket, the state of the socket, what is the host address, host port, destination address, destination port, and these are the buffer sizes. So this is the send buffer size, and this is the receive buffer size. And finally, you can combine all of this. So you can do sockets, PS3, files, PS3 env, and you're going to get this absolutely humongous tree of pretty much all possible data that you can think of wanting to know about anything and everything that's happening inside a container. So yeah, that is pretty much it. Any questions? Do we have any questions?
Yeah.
Thank you. Hello.
Hi.
So, does it need any special flags to inspect the CH-rooted namespaces?
So CH-rooted namespaces inside containers can be directly accessed via the GoCRIU library. But if you have CH-rooted namespaces in a native Linux process that you're trying to checkpoint, the checkpoint would not work, unless you're running CRIU as the root user. If you're running it as the root user, everything's going to work.
Hello.
I can't. Hi.
Yeah. Hi. So I just. Okay. So I just want to ask, how do we maintain the integrity of GZ file over there? So if some user extracts the content,
Right.
deletes something or changes something,
Right.
and then again repacks it.
Yes. Yes.
So how do we have the integrity maintained?
You can, use an MD5 hash, or you can use a SHA-256 hash. Sorry? Yeah, it's left to the user. So currently, this is not a feature being offered, by the checkpoint facility integrated into these container runtimes. It's left to the user to verify and sign the checkpoint archives that are generated by the runtime.
Thank you.
Does it checkpoint all the namespaces, like time, space, and all those things?
I'm sorry?
Network. Does this checkpoint all the
Yes.
namespaces?
Yes. So CRIU supports checkpointing any namespace associated with the process itself.
Okay.
It also supports C groups. It supports active network connections. So when I say active network connections, I mean, let's say you have a TCP connection and you're streaming some data. It also checkpoints whatever is intermittent, like being passed through that socket without actually reaching the destination. So it also stores the TCP stream on both the receiving end and the sending end.
Thanks.
So does it also report the zombies?
Yes. So for zombie processes, CRIU creates dummy files that are used to represent it. And similarly, let's say your process accessed the file and then that file was deleted, but the file descriptor for that is still open. It creates something called a ghost file in that scenario, where it uses the existing information about that file to infer the size and just creates a dummy file of that particular size. So this just ensures that when you restore the process, you still retain the file descriptor even though the file itself doesn't exist anymore.
Okay, great. Do we have any more questions? No. Thank you so much,
Thank you.
Prajwal, for your wonderful talk.